Alright, so I accidentally detonated this malware, and what is going on, dude? Oh boy. Moral of the story is don't infect yourself with malware. It is time, part 3 of the Complete Malware Analysis Project 101. In today's video, we're going to be detonating and dissecting the prolific Zeus banking Trojan. Now, in this analysis, we're going to be conducting some basic static analysis, running through, seeing if we can find any things of interest. We're also going to look at the assembly level code very briefly, and then we're going to go into dynamic analysis where we're actually going to run the malware and see what is going on within our machine. We have a lot to do in today's video, and really a lot of this is going to be basic, but it will equip you with the right set of knowledge, tools, and methodology to go out and dissect your own malware. So let's go into the lecture slides, and I don't know, we'll see what happens. Hello and welcome to the Complete Malware Analysis Project 101. In today's video, we're going to be dissecting and analyzing the prolific Zeus banking Trojan. So with that being said, let's overview what we're going to be doing in this crash course. So if you haven't heard of the Zeus banking Trojan before, I'm going to be providing a bit of background information on Zeus and basically what happened. Next, we're going to be overviewing the analysis tools in some lecture slides, what we'll be using in today's video to actually go through and dissect our malware. Next, we're going to be provisioning our lab, and then finally, we're going to actually go and conduct our analysis, which includes downloading the Trojan, labeling the malware, and then going through with basic static, dynamic, and reporting and indicators of compromise. So we have a lot to do in this crash course. So before getting into the Zeus banking Trojan, what should you have done by the time you start this crash course? First is the malware analysis that is built. In the previous video and lectures, we went through and developed our own isolated malware analysis lab, both through a self-hosted solution and cloud-hosted using AWS. I'm going to be using the self-hosted VirtualBox way with virtual machines as denoted by the arrow, but of course, you're welcome to use the cloud-based version as well. Next is a snapshot of the base image. So if you're using VirtualBox, you should have two virtual machines, the Flare VM machine and a Remnux machine. You want to make sure to have a consistent base image called a snapshot, which we can revert back to if we need to when detonating the malware to have it at a clean state. Now, if you haven't done this already, what you're going to want to go ahead and do is go and navigate to your Flare VM virtual machine, go to this little bar here, and then just click Snapshots, and then you can click Take. But before you actually go and take the snapshot, go to Settings, and ensure that in the network settings, you have host-only adapter, and you have the virtual host-only Ethernet adapter applied. Once you do that, you can go ahead and proceed to take the snapshot image and call it whatever you want. I call mine Flare Base VM. Whatever you want to do it, it's up to you. For the AWS lab, you actually won't need to create some sort of snapshot because of how Terraform works. It's immutable infrastructure, so you can just go ahead, do a Terraform destroy, and then a Terraform apply to re-provision your lab. And finally, you need an established internet connection where we're actually going to go out and download the Zeus banking Trojan version onto our virtual machine, and then we're going to detach from the internet. I'll show you how to do that safely here in a few moments. So in today's video, we're going to be dissecting Zeus, the prolific banking Trojan. Let's provide a little bit of history on what the Zeus banking Trojan is. So it primarily was created to be a financial banking Trojan, and it was spotted way back in the wild in 2007 when the US Department of Transportation identified some malicious programs on their computers. Now, since then, there have been over 573 plus versions of Zeus. And actually, there's this cool website, zeusmuseum.com, where you can see the different families and track the different versions of the Zeus banking Trojan. Now, the reason why this happened was because malicious code that made up Zeus became public in 2011 after a leak. And well, that created a whole bunch of new mutations of the Zeus banking Trojan. Now, it is suspected that This individual here, which I won't even try to pronounce their name, is the author of the Zeus banking Trojan. He has a $3 million bounty from the FBI and still to this day continues to be one of the most wanted hackers, even after more than a decade of this program being out in the wild. So, the goal in delivery methods. The goal of the Zeus banking Trojan, as the name suggests, is to steal people's financial information and exfiltrate that sensitive information where they could go out and use that information. But secondly, there was variants that had a peer-to-peer botnet system where when a machine became infected, it'd be a part of a huge network of botnets. The delivery method depended on the variant, but at the very beginning of the Zeus banking Trojan, it really was through drive-by downloads and phishing and spam campaigns. Now, drive-by downloads basically require a user to visit a website that has some sort of backdoor Trojan code on it. Now, this attack vector is really obsolete in today's day and age because web browsers block these downloads by default. The Zeus banking Trojan, to this day still, is delivered through phishing and spam campaigns, but ultimately has had this be an infection method for many years. All right, so ultimately, the Zeus banking Trojan became a prime target for the FBI. Specifically, the Game Over Zeus version, which was a very prolific version of Zeus, was a target for the FBI. And by that time, there were 1 million computers infected, and 25% of those were in the United States. And by that time, also, 100 million plus dollars worth of financial damages were due to Game Over Zeus. So the FBI tried tracking down the author. They identified this individual. He still has that $3 million bounty on him. Now, what is the impact of the Zeus banking Trojan? Well, first off, it inspired hundreds of additional variants which use parts of its source code. And also, millions of people's machines were infected with associated costs in the millions. And of course, there was financial information that was leaked, impersonation, and really a lot of impact had happened just from, well, a banking Trojan. With background information behind us, let's overview all of the tools that we will be using in today's dissection of Zeus. We're going to first off start out with VirusTotal. You may have heard of this tool before. Basically, it's an analysis tool which allows us to upload files, programs, maybe input domains and IP addresses, and see if they are malicious. And how this works is that it aggregates all of the various antivirus products and online security scan engines and sees which of those AV engines have flagged it as malicious. Now, VirusTotal is used to fingerprint a malicious sample and really measure its functionality against established security engines. You always want to make sure to upload files and sensitive information, which, well, isn't sensitive. So basically something that isn't proprietary to you or your company. Next is PE Studio. PE Studio is going to be used to statically analyze malware and identify artifacts of interest. Specifically, we're going to be collecting static information, including hashes, file headers, file properties, strings, and much more. It's a very easy to use program. All we will need to do is drag and drop the Zeus binary or executable into PE Studio and let it do its thing. All right, so next is Floss. Floss is a basic command line utility which allows us to extract strings from executable. Now, why would we want to extract strings? Well, strings are compiled in programs and could possibly include information about URLs, imports, IP addresses, and other functions hidden inside the program. And Floss specifically is a really advanced tool because it automatically deobfuscates strings from malware binaries. And one common technique used by malware is called packing, where authors will pack or compress their malware to obfuscate the valuable information or hide those strings from malware analysts like ourselves. And this makes it harder for us. Well, Floss has these really cool built-in algorithms that go out and try to deobfuscate the strings for us. And it's simply running Floss, malicious executable, and then pressing enter on the command line. Next is going to be Kappa. So Kappa automatically detects capabilities of the program and outputs what it thinks the functionalities of that program are. It's a simple command line utility program, which allows us to supply the program executable and see what happens. Now, rules are matched against known API calls, identified strings of interest, and much more. And the behavior from Kappa output can be mapped to the MITRE ATT&CK framework. Next is Cutter. Cutter is a reverse engineering platform, and we're going to be using Cutter to view assembly level instructions of the program and actually view the completely decompiled code. So we're going to be getting really low level into assembly because assembly has no other layers of abstraction. So it is the baseline programming language, if you want to call it a language, which has no abstraction. So we're going to add the Zeus banking Trojan into Cutter and look through the assembly level instructions from a very high overview in today's video. Next is inetsim. This is our first dynamic analysis tool where we're actually going to go out and run the binary. So inetsim is basically a service used for simulating common internet services. And really, it's going to be used in today's analysis for impersonating a DNS server. So it is as simple as running inetsim on the command line in Remnux, and that will impersonate DNS for us. Next is Wireshark. Maybe you've heard of Wireshark before, but basically it's a network packet sniffer and analyzer. It's used for network troubleshooting, packet analysis, and for malware-specific use cases, we're going to be viewing the ingress and egress network traffic from the malicious program and maybe flag any particular domains or IP addresses being reached out to within the hidden binary. Process Monitor, or Procmon for short, is a part of the sysinternals suite, which is a set of programs that Microsoft actively manages. And really, these programs help you do a lot of things just in the Windows world. But specifically, Process Monitor is going to allow us to monitor and display real-time information on what is happening within the Windows file system. So it can capture a lot of different events, including what's happening in the registry, the file system, network, processes, and profiling events. And specifically for malware, it's going to allow us to capture maybe malicious activity occurring within the file system, such as when it sets arbitrary registry keys or writing files to Windows paths or anything that is of interest. And Procmon does a really good job of capturing that information. Next is YARA. YARA is used to classify and identify malware samples by creating rules of what malware families are doing, and it's based off of patterns or textual information. So YARA rules are written as one that is in front of me, like here. Basically, it extracts different information, maybe strings of interest or byte sequences, and these variables are evaluated by a condition block, which implements logic. So, for example, if this file is named this particular file name, pdf.exe, then, well, it matches this YARA rule. Okay, so now that we have overviewed the tools, as I've said, I'm going to be using our VirtualBox VM network, which has two virtual machines running. One is Flare VM, two is Remnux. It's going to be isolated in the host-only adapter, which has no internet access. Finally, some warnings and disclaimers. First off, safety is key when dealing with malware. Ensure you are always following protocols when it comes to downloading and detonating a malicious sample. Follow all the instructions listed within the course. And then disclaimers, of course, personally, I cannot take responsibility if you infect your host machine or any other machine or network. And two, this project and the set of videos is for educational purposes only. So I'm not here to try to show you how you can write your own malware. I'm literally just trying to show you what malware does. So with that being said, let's get our lab up and running and download the Zeus Banking Trojan. Oh boy. All right, so here in front of me, I am in front of VirtualBox Manager. I have my two virtual machines turned off here, Flare VM demo and Remnux demo. Now, like I said, make sure to take a snapshot if you have not already, and I'm going to proceed to just turn these on and wait until I get to the desktop. Alrighty, so I have my two virtual machines powered on here, and what we're going to have to do is download the Zeus banking Trojan. Now, based off of last time's lecture, we went ahead and created a snapshot where we had host-only adapter configured in both of these virtual machines, which means that they can talk to each other, but they can't reach anything else, the outside internet, for example. What we need to do is proceed to turn on internet connection for our Flare VM host momentarily, download the banking Trojan, and then turn it off. So going up to machine settings and down to network, we can choose NAT or bridged adapter. I'm going to choose the bridged adapter. All right, so here we can see that network 2 is connected. We have internet connection. Let's proceed to go to Microsoft Edge. So the Zeus banking Trojan is located out on the Zoo, which is a GitHub repository which hosts a whole bunch of different malware samples. Based off of the previous lecture, you may have enabled the bidirectional clipboard, which allows you to copy and paste text and URLs from your host machine into your virtual machine. Now, to enable this, just go to General, Advanced, and make sure that it is bidirectional for both. Click OK, and I'm going to be pasting in the link to the Zeus banking Trojan. You can find this in the description below. So here we have 4 files in this repository. As you can see, one of these files is a .zip file. This is something to be noted. Every good malware analyst compartmentalizes their live samples into compressed or archived files such as zip. What this does is to ensure that even if you were to download this here, you're not detonating the real world sample, and it just is a safety precaution. So what I'm going to proceed to do is click the .zip, then go to the download icon. Now, you must note here that I am using Microsoft Edge. If you go to Google Chrome and try downloading this, it's going to block it automatically. So I just go through and use Microsoft Edge for just downloading the banking Trojan. Now, we can go in to the file or folder icon. Take note of where this is at, which is going to be in the downloads folder. And then at this point, go to Machine Settings, Network, Host Only Adapter. So we're cutting off internet access immediately. At this point, we have no internet access. It's going to say no network or no internet identified. So at this point, we are good. What we can do is take our zip file. Of course, I've downloaded this twice for the sake of demonstration, but I'm going to go and drag and drop this to my desktop. The Zeus banking Trojan zip is in our desktop. What we're going to do now is proceed to take another snapshot. Machine, take snapshot. I'm going to call this Flare VM Zeus. Click OK. And wait. All right, so we want to make sure that our internet connection is disabled. We can go up to the Zeus banking Trojan, right click, under 7-zip, which should be installed with Flare VM, choose Open Archive. And here we can see this interesting file, .pdf.exe. Let's drag and drop this onto our desktop. Now, as a second safety measure within our zip files, we have a password. We want to make sure that we know what we are proactively doing. So this is yet again another way to make sure that the analyst isn't, automatically or somehow mistakenly produces this malicious binary onto their system. So we know that we have no internet connection. We are on a virtual machine. We're good to go. So we can type in the password. For all binaries on the Zoo GitHub repository, the password is infected, all lowercase. At this point, we are good to analyze. We can proceed to take another snapshot if we want to. But at this point, I'm going to stay here, and this is where it gets fun. So let's go ahead and start out with basic static analysis, first by using VirusTotal. All right, so let's proceed to fingerprint and identify what this malware is. First off, I want to note that in my host machine, I have a Word document that has a report template of what we're going to be doing. We're going to be fingerprinting and then going through static, dynamic, and then also going through a YARA rule. So we're going to iteratively go through this process and add in details, meaning we're going to be building the report while we analyze this malware. So going back into the Flare VM machine here, again, we have the invoice. What I'm going to do first is by using VirusTotal, we can see if any of the security vendors with their security engines have ever seen this sample of malware before. Now, you will need an active internet connection, meaning you will need to go back into the settings here, machine settings, and change this to either NAT or bridged. This will connect us to the internet. If you're afraid of having internet connection while there is this file on the file system, you don't have to do this step, but you are going to be safe as long as you're in the confines of a virtual machine. So going down to Google Chrome, let's look up VirusTotal. And VirusTotal makes this really easy. All you need to do is just choose the file name and go to desktop, invoice, open. All right, so as you can see here, this sample looks like it's been seen before. 65 vendors are flagging it as malicious. And what's cool about VirusTotal is that you can go through and see which vendors have flagged it as malicious. And really, you can get to also see perhaps what this name is called. So some call it Zbot, others call it Trojan. And it's just an interesting way to look at this. Even go to the details section, and here you can actually see the hashes that are outputted when you put this sample in. And then you can even see the behavior if you really wanted to. So for the time being, let's go back to the detection. And on my host operating system here, I'm just going to open up the snipper tool. You can use whichever screenshot tool you like. And I'm simply just going to screenshot this right here. All right, so VirusTotal output. We can do formatting later. Right now, we're just trying to collect the artifacts. And the reason why we're doing the report iteratively is because, we want to kind of identify and take track of our steps just in case we get lost or maybe we need to revert back to a state. So I like to go through and do malware analysis and basically just document my steps as I go through. Okay, so going back into our Flare VM virtual machine, at this point we can minimize out of Chrome, and let's remember to go ahead and, change the internet connection back to host-only adapter, and then make sure that you have your VirtualBox Ethernet adapter. It's either going to be 2, right now I have 3, but if you created it from last time's video, it's going to be number 2. All right, so our fingerprinting isn't done. Based off of VirusTotal's output, we know that this sample is malicious, and we can even go to the Details tab. We have these hashes. Now, one of the reasons why we want to hash our file name or our malware sample is it provides uniformity when you are giving this sample to other malware analysts, and also when it comes to security engines, when you have something that is able to have static information, which is a hash, something that doesn't change, you can give this to a security engine, a malware analyst, and you know that you're working with the same exact sample. So here we have 3 different types of hash algorithms, and we can copy these over into our report. Now, we're actually going to use PE Studio to develop these hashes. So if you go down to your search bar and search PE Studio, you should have PE Studio, and you can just accept user access control. Now, as I said at the beginning of this video during the lectures, PE Studio is really easy to do. All you have to do is go in your invoice and just drag and drop. All right, so what's going to happen here is once you get the file in, you're going to see some different tabs, and this may take a few moments to generate the information. Now, PE Studio offers a lot of granular information into the executable. And executables often are called binaries or programs. So I'm going to be calling it a binary from here on out. But basically, when you're talking about an executable or aka a program, an application, it's also a binary. So if we take a look in here at PE Studio, we're not going to go through everything here, but the first thing that we're going to want to identify is the hash. Now, what's really cool about PE Studio is that we can actually go to the hash, and if we hover over this, this is going to give us a virus total link, which we can copy and paste into our browser if we did have internet connection. Now, we don't have internet connection, and at this point, we are okay, and we're actually just going to copy all of this information over as another means of fingerprinting our malware. So clicking these, followed by a shift, right-click, and just do copy lines. And then going back to our host operating system and adding in our hashes as another way of fingerprinting this sample of malware. All right, awesome. For our final fingerprinting, we're actually just going to take note of the name of this sample. So it looks like this is trying to impersonate some sort of maybe company invoice. Maybe this was delivered through some sort of phishing campaign or impersonation where they're trying to impersonate a company invoice. So what I'm going to do here is right-click and go to Properties. And I'm just going to simply copy and paste this name here. Now, you're also going to notice something. One of the things here is that it looks like it's trying to impersonate a PDF document, but as you can see, this has a double formatted file. So you have a PDF and then you have .exe. What this really means is that this is an actual .exe, but it's trying to impersonate a PDF. So let's go and type in the file name. All right, awesome. That's good enough for our fingerprinting. At this point, let's proceed into basic static analysis. Okay, so with basic static analysis, what are we trying to do here? Ultimately, we're trying to examine the program and code and identify maybe any malicious artifacts without running the actual program. And what this can allow us to do is fingerprint the program, maybe write some detections if we wanted to, which are unique to this particular program. And maybe we're just trying to understand what's under the hood within this executable or binary. So what we're going to be doing is employing a few different tools to gather information for us. The first one being PE Studio. And we already have the PE Studio output here. So I'm going to go ahead and click OK. And in PE Studio, we have, like I said, all of these different tabs. Now, we're going to try to find some strings of interest, anything that maybe pops out. This could be a URL, a domain name, maybe an IP address, or maybe some different types of imports, aka like DLLs or something like that, right? So first off, I already noticed something that's sticking out. If you look at the export, you have something called correct.com, but it doesn't actually have the right spelling. And this is really interesting to me. Why is this program have correct.com embedded in it? I don't know. We're going to have to take a look into correct.com later. So what I'm going to do is just note this right now, taking a screenshot within PE Studio and adding this to our report. All right, so within PE Studio, the first section we're going to go into is actually, it's called sections. Here you're going to see a whole bunch of information, and in my opinion, it's a lot of gibberish. Now, in this sections, what we're trying to look at is the file size of this program. And here you can see the different headers and their different names to the headers, .text, .data. And specifically, let's look at the .txt. Now, here in the property columns and rows, you're going to see a raw address and a virtual address. What this is denoting is how big the file is. Now, in the comparison of the values, you can see that this says 46,000 and this says 46,000 bytes. The reason why we're trying to compare these two is to understand whether or not this is compressed or packed. The way to maybe figure out if a malware is compressed, it's packed, is to see if these two values are similar. If they are, that likely means that there is no sort of compression or packing going on, which malware authors will do to make sure that you have analysts not coming in and trying to understand the functionality of their malicious programs. Now, if the raw size and the virtual size are much different, then that may mean that this malware binary is packed. The virtual size will be much, much bigger than the raw size. And really, what this means is that the raw size has the core functionality of the program, what it's actually doing. And then you have the virtual size, which is just putting a whole bunch of gibberish or code that's trying to obfuscate the overall functionality of malware. So in this case, what this probably means is that this program is not packed. All right, so going down to Snipper, let's get this thing, and, well, we can write that up later as an artifact that we found. Okay, so next, let's go into the strings part. This is one of the best parts of PE Studio. So in the PE Studio output, it's going to have all of these strings that are outputted. Basically, it goes through and tries to extract all of the plain text and anything that is contained within the binary. So a lot of this is just going to be a whole bunch of random sequences of characters and strings. One of the first things that you can see when you go up to the very top is you have all of these interesting function calls. For example, this one really sticks out to me, get capture. That most likely means get the screen capture or take a screenshot. You have write file, maybe writing a file to the file system. What's cool also is PE Studio will flag these as being malicious, right? So you'll have programs which may be malicious, and it has these flags. And here you can see all of the imports, the functions that have been flagged. So, get clipboard or winexec or write file. So this is definitely something to take note of. Most likely this is hinting at the functionality of this program. So maybe this program can, get a screenshot, copy the contents of the clipboard, stuff like that. What I'm going to do is take the first row, go all the way down to where it has the last import. Now I'm just going to copy the values here and put this in my report. All right, so full screening this here. Let's proceed down and see if there's anything else that is of interest. Like I said, we're trying to look for maybe anything that has any program or URL or IP address, anything that sticks out to us. All right, so this is another interesting artifact. If you take a look here, you have these random string of characters, and then below it, you have kernel32 mul div. I don't know what that is. I don't know what kind of functionality it is, but it most likely means that this is a function embedded within the kernel32 DLL. Here you can see this random gibberish and then also the kernel32. But then you can also see the user32 DLL and the function here. And something that is maybe a little bit more easy to read is a create file. So this is a function that's embedded within probably the kernel32 DLL. DLL stands for a dynamic library link. It is a part of the Windows ecosystem, and ultimately think of DLLs as a means of sharing code. So different programs and developers can use DLLs to import various functionalities. as an example, in the kernel 32 DLL, there is a function called create file, which allows you to create a new file on the file system. What's interesting to me here is how each of these characters have some sort of random gibberish, and then they have the user32 DLL. They're using various functions embedded within the DLL. What this makes me think in this case is that perhaps this is a function name. So whichever native language this program was written in, perhaps they use these random function names to obfuscate what is actually going on. And each of these functions will use the DLL components. So what I'm going to do once again is just a simple copy, go all the way down to the bottom, and copy these lines, and then put this in my report. Now, you may be wondering, how am I actually going through these strings? I've already went through this analysis of the Zeus banking Trojan. So the first attempt that I did at this, I was actually just going through and looking line by line. I know what I'm looking for in this case for the sake of demonstration and time efficiency in this video. But in the real world, what you're going to want to go out and do is just go through iteratively the strings and see if there's anything that maybe sticks out to you personally. So at this point, I don't really see anything else. Haven't made it all the way to the bottom. All right, so making our way to the bottom, I don't see anything else that sticks out to me personally here. Perhaps some of these values could be encoded. We really don't know, but at this point, I think we have enough of the strings that we can probably continue forward. If we go to the libraries, you can see that based off of the string section, there's 3 different DLLs being used. Kernel 32 DLL, user 32, and then the shell WAPI DLL. So perhaps these, well, you can see here, shell lightweight library, the Windows NT base, and something else. But basically, there are 3 DLLs being used within this program. All right, so going back up to the top, I also wanted to highlight here, PE Studio will give you the first sequence of numbers for the hex dump of the file. So basically, the file is represented in hexadecimal format, and as you can see, MZ means that it's an executable. All executables start out with the initials MZ. So we can keep this as an artifact if we want to as well. I'm just going to take a small little screenshot, and I'm going to add this into the fingerprinting section. Scrolling back down to my basic static analysis section, I'm going to take note of those libraries that we see in PE Studio. I'm going to do a simple copy and paste to make sure that, let's do this actually. All right, that is good. All right, so for our next tool, we're going to use Floss, which is also a command line utility which outputs all of the strings contained within the program. Now, I recognize a simple glitch here. I'm not sure what's going on, but what I need to do is proceed to actually exit out of PE Studio, and this will allow us to open our terminal emulator, which is going to be Commander. So if you just do cmd followed by enter, you're going to see that this is basically a terminal emulator. It's a more enhanced terminal emulator compared to the standard Windows that comes by default. So here we're in the C users grant directory. Let's change our directory into desktop and just perform an ls. Here are all of our files, and the invoice PDF exe is what we're looking for. So like I said, Floss is a command line utility that outputs all strings of interests. In the lecture slides, I also mentioned that Floss does some cool deobfuscation in the background. Now, because this binary likely is not packed, it won't have to use any of those tools or tactics. But for the time being, what we're going to do is simply add in Floss, followed by the name. I'm going to use tab completion, and then I'm going to use output redirection into a file. We'll call this strings.txt. All right, so we're going to let this do its thing and wait until we get our command line prompt back. All right, so minimizing here and going into strings. All right, so what you're likely going to see is something very similar to what you've already seen in the strings section within PE Studio. And to confirm, we can go through all this. Here are those function names that we had flagged, and followed by the Windows 32 DLLs and these random function names. That's what we're suspecting at this moment in time. Now I'm going to use the Control F functionality and look for anything that has a .com, see if there's any hard-coded URLs. Now we're seeing correct.com or CRECT, so that means it's also embedded within this binary. We'll do some follow-up analysis on what this domain is and whether it's malicious or not. All right, so it looks like that is it for the .coms. We can do like a .net or a .org. Not seeing anything there. So let's exit out of our strings output, going back into our commander prompt here. One feature I want to highlight about Floss is that you can also extract strings which are a certain number of characters or above a certain number of characters. So for example, if we did Floss and do a -n, let's say we want to do 6. What this will do here is output all strings which are above 6 characters. All of these will be above 6 characters. So it's just something to note about Floss. If you're trying to look for maybe a hard-coded URL, or you're looking for characters that are equal to or above, you can use the -n flag option. All right, so that is it for Floss for the time being. There is one more tool we're going to use, which will hopefully maybe show some functionality and map those functions to whatever the heck it's going on within the program. So what I'm going to do is go down to my search bar again and open up PowerShell. Full screen this. Okay, so there is this command line utility called Kappa, as I'd mentioned in the lecture slides. Now, Kappa has some different flag options. As you can see here, there's a -v, there's a -vv. For the time being, let's just supply the file name. So going into the desktop directory, and then doing a kappa followed by the name, if I can spell right, tab completion. So here in kappa, as you can see, the hashes are output, and we saw those in VirusTotal. We calculated those in PE Studio. Here is the file name. We can see that the format is a PE, which stands for Portable Executable, and that this is made for a Windows system. We know all of this now. What's unique about Kappa is that it maps or attempts to map to the MITRE ATT&CK framework. Now, the MITRE ATT&CK consists of the tactics and techniques used by various malicious programs, APTs, threat actors. It's basically a huge matrix of behavior that can be mapped to. So for example, here you can see the attack tactic is defense evasion, and the technique in this particular case is virtualization sandbox evasion. So somewhere within this program, there is some virtualization or sandbox evasion. And of course, what that would do is to make sure that we don't have malware analysts like ourselves coming in and looking at the binary. And you can see this little code here. We can actually take a look at this code. I'm going to right click to copy, read more about what virtualization or sandbox evasion is, and maybe some different threat actors that have used this before. I'm not going to take a look at this in particular right now. Okay, so going back into our virtual machine, you can also see that there is this objective anti-behavioral analysis, virtual machine detection, and here are some capabilities that have been mapped to. VM detection, PE, and I don't even know what this is. So let's go ahead and clear the screen, and in this case we're going to do a kappa, and this time with a -v, and then followed by our file name, tab completion, hit enter. So the -v option will give us some different output than just the standard kappa. Here, it's just going to do it in more of a readable manner, I guess. So you can see what the base address is. You can see more information on what is happening. So in this case, it gives you the namespace. It gives you basically the same type of information as before. Now, what's really cool is that when you go and do a kappa-vv invoice followed by enter, this will show you within the code where it thinks the binary is employing the different strategies. So the -vv option will output some more verbose information about where it thinks the capabilities are within the binary. So it will actually map where and flag where these sandbox evasion or defense evasion or whatever type of a tactic or technique is being used, and it will map it to where it thinks it's within the binary. So the function at this address space or the function or section at this address space highlights this particular behavior. Here you're not seeing much in this particular binary, but it's just something to keep in mind when you are analyzing different samples of malware. So what I'm going to do is proceed to do one more kappa, and I'm not going to use any other information. This is going to be for the sake of collecting a screenshot for our report. So going down, I'm going to use snip tool and capture this, paste it. Going up to the top of our report, first off, we have our fingerprinting information that we have collected. There's really nothing we need to do here. Perhaps one of the things that we know is that this is a portable executable or binary file, and it's native to Windows. Scrolling down to basic static analysis section, this is where we can start collecting all of our information and seeing what the functionality of this Trojan is. First off, we have this interesting domain. It's called correct.com. I don't know what this is or what we're looking at, but what I'm going to do here is go down to my host operating system. I'm going to go to VirusTotal again and look up correct.com. In VirusTotal, you can go to the URL section and let's supply correct.com without 2 R's. All right, so this is interesting. There are no security engines flagging this as some sort of malicious domain. One of the things that I also like to do is go to the Wayback Machine. And I already put this in here based off of my previous analysis. As you can see, there are all different types of snapshots. Now, I'm going to go to the 2013 year, given that this file name from the zoo was November of 2013, and I'm just going to pick a random day. Let's do February 3rd. Let's see what this website contained on this particular date. All right, so it looks like this is some sort of news website, and I don't know. Let's see here. Copying this text into Google Translate detected it as a Romanian domain, or perhaps, I don't even know what this is, but let's actually look here and go to interesting. So correct in Romanian is correct in English. Interesting. Let's see, what about correct? So that yielded no particular information. So for the time being, what I'm going to do is minimize out of my host machine, going back into my report, and I'm just going to say correct.com yielded no interesting results. Okay, so our next set of information is these interesting imports. If you recall from the PE Studio output, this was a part of the strings section at the very beginning. And as you can tell, these appear to be different functionality. Now, I would think that these are API calls of some sorts. All right, so what I'm going to do here is do a little bit of formatting on my report end, and I'm going to make sure to just keep in the API call, what I suspect is the API call, and delete all of this other information. For the time being, this isn't useful, and I don't think we will need to use this. So what I'm going to do is write API calls and format this. For formatting all of these different API calls, here is the list that we receive. So as I said here, this allows us to understand what is going on or the capabilities that the banking Trojan uses. Now, some of these are self-explanatory, such as perhaps write file or find next file or set the foreground window or get environment variables, but other of these are kind of interesting. Now, some of these I don't really know what is going on. For example, get async key state. So I'm just going to copy this, for example, and using the powers of Google or ChatGPT, whatever you want to do. Here you can see that this is a part of the Win32 API, and specifically it determines whether a key is up or down at the time the function is called. So I can just proceed to copy this and paste it into our report here. So for the API calls that I perhaps don't know, I could add in a little description, look these up on the Microsoft documentation. I'm not going to do this for all of them, the ones that I don't know. You're welcome to go look at the ones that maybe are not self-explanatory. But the overall functionality, it appears, is that it's pretty powerful. It can capture screenshots. It can get the clipboard data. It can get the environment variables set within the Windows environment. It can write files. It can read files. It can see where the file paths are, the drives. There's a lot of different functionality within this Trojan. So this is a very powerful program once it's most likely executed. Okay, so moving down into our next section, this is where I suspected during my first round of analysis that these random sequence of characters followed by the DLL and then the dot have something to do with a function name. So what I'm going to do here is I'm just going to look up kernel32 moldiv. All right, so it appears here this is what moldiv is. I don't know why you would want to use this, but perhaps there is some sort of valuable information. I'm really not sure. So what I'm going to be doing in this particular case is, again, formatting all of this data so it looks a little bit better. I'm going to keep the random gibberish, but I'm going to delete all of this information here to format it. All right, so after applying formatting here, you can see the suspected function name followed by what its functionality is. You can start to see here that, well, let's see, for example, the third one, kernel32 set the current directory. So perhaps that is a functionality that this function provides. Now you may be wondering, why did I suspect that these random sequences of characters are functions? Well, one common technique used by malware authors is to obfuscate the overall functionality of their code. Like I've said before, they do this in a lot of different ways. Perhaps one of the ways that this author of the Trojan virus did was to create random sequences as function names. So instead of naming this as perhaps destroy icon as the function name, they decided to use this, which is a probably random generated sequence of characters. Now, scrolling down, you can again start to see some of the functionality that perhaps this code provides. So here, maybe this is the actual code that contains what the program can do. And then if we scroll up to the API call functions, these are the APIs that are leveraged. And so this gives us visibility into all of the functionality of this particular Trojan. This is all kind of interesting information. Now, for the sake of simplicity and time, I'm not going to go through each of these ones, but of course, you're more than welcome to pause the video, scroll through these, and then look these up on the Microsoft documentation. All right, and then finally for the kappa output, I'm just going to type in this, and this is the techniques that have been used. So we know there's some sort of virtualization, sandbox evasion going on. All right, so at this point, we are ready for some basic advanced static analysis, and we're going to do this using the tool Cutter. All right, so back in Flare VM here, I do not have internet access, and I'm going to proceed to get internet access back because, unfortunately, Cutter does not come pre-installed with the Flare VM toolset. All right, so I'm just going to download Cutter and run through the default installation until I have Cutter installed. Okay, so I have decompressed Cutter into my desktop. Here I have the Cutter executable. You can choose to put the Cutter file wherever you want to. Know that it will be zipped up, so just make sure to drag and drop the folder into your desktop. I'm going to proceed to fire on Cutter here and choose Run Anyway. So Cutter offers a lot of advanced capabilities, and for the sake of this video, we're going to be doing some basic analysis of this program in Cutter, which is going to show us all of the assembly code. Now, it won't let us run the program, but at least give us visibility into what is going on. So I'm going to choose Continue here. When opening the file, we're just going to open Invoice, then choose Open. Leave these settings as default and just press OK, and then we'll wait for this to load in the executable. All right, so as you can see here, it gives us the hashes just like a lot of other malware analysis programs. It provides the 3 libraries that we extracted from the strings section. Gives us the format, the bits. Looks like it's a 32-bit program. And, just some other interesting information, 523 strings. Here on the left, we're going to see a whole bunch of functions. So each of these functions is going to contain its own set of assembly code. Here we can see the entry point for this program. We can double click it. This will actually output the assembly code for the program. So this is the entry point into the program. You can drop down and you can see the offset or the memory address location. And you can see the instructions here. Now, a lot of this just looks like random gibberish. In fact, when you're reading assembly code, it can be very confusing. And typically, I get out a pen and paper when I'm actually running through assembly code. Now, for the sake of this course, what we're looking at is just anything that maybe sticks out to us. Now, within the entry point, one thing that I already have noticed, you see this allow set foreground, get tick count, or any of these other, well, they look like API calls. It appears this is where the API calls are located for specific functions. There's another interesting API call. So going back into our report, let's see if that allow set foreground was within our API call section. All right, here it is. Now note that when we went into the entry point, it was the first API call that at least stuck out to me, and it's the first API call that was outputted based off of our strings command that we took out of PE Studio. So it's likely that this is following its probably same sequential order of API calls. I do want to highlight this here. Get tick count. What would this mean in a malware binary? Well, get tick count is typically a mechanism employed to see how long a machine has been powered on. So this is an interesting artifact here. What's really cool about Cutter is that they give you this graph view. So this is just the instruction set. You go to graph, and here you can actually see the order of execution. So scrolling all the way up here, go all the way up into the entry point of the program. You have all these different instructions. And basically, based off of the results within each of these blocks, it will either proceed to the next instruction, or, as denoted by the arrows, it will jump. So for example, the output of this will either make it go into this block here, depending on which result it is, or it will skip and go to this block. So that's something just to take note of. All right, so like I said, this get tick count probably means that one of the mechanisms that's being used within this binary in particular is that it's seeing how long the Windows machine has been running. So if you're in a virtual machine environment, it's likely that your PC or your virtual machine hasn't been powered on for that long compared to your host machine. I'm going to take a screenshot of these 3 blocks here just as a means of documenting what we found. All right, so scrolling to our advanced static analysis and just pasting that in. What's also really cool about Cutter is you can go to the decompiler tab down at the very far right. And this will give you the instruction set in a little bit easier to read format. Now, remember when we went back to our report and we found these different gibberish random sequences with these DLL files followed by probably some sort of function contained within that DLL. I kind of want to see where these are located within this binary. This particular function here seems interesting to me, creating a file on our host. I don't know why, but it just makes sense to me. So what I'm going to do is try to put in this string into Cutter and see if it will resolve into anything. It probably will not. So it does not appear it does. I can exit out of here. Let's go into the entry point again. And scrolling down, I'm just looking for anything that's of interest. Notice that this provides the same string output as the other programs that we have used here in the past. So instead of putting the cell random sequence of characters, which we think is a function name at this point, into here, I realized I was doing that wrong. This is the functions tab. Let's go into strings and let's paste this in here. And as you can see, gives us this output. Let's see if we can jump to it. Alrighty, so as you can see here, it looks like part of the string IGH capital C is there. So we've located at least a part of this sequence that's in the cell roto here. Specifically, this sequence right here is what is being reported in Cutter. Now, what I want to see is this function name similar or in a close proximity of the kernel32 create file? So going back into Cutter and let's go to strings. All right, we're trying to do the create file A. All right, so now notice how close in proximity the string sequence IGH GHC is to the instruction of kernel 32 create file A. So I'm doing some hypothesizing here. I can't confirm in Cutter specifically, but what I think this is that the function names, given the close proximity to the DLLs, most likely means there's some sort of capability going on here. Whether that is that these are function names, I don't know in particular, but I'm going to suspect that this is obfuscated function name values. So I'm going to take a screenshot denoting that this here is where the kernel 32 function is located, and then this is where that function string is. Now, as I've said here, I can only suspect that perhaps these random sequences of characters are somehow function names. I don't know in particular, and right now I could not tell you if it is. So the power of Cutter really is showing what is underneath the program. So we're actually seeing the basic instructions, and Cutter provides all of these different nice menus, including a decompiler, a hex dump of all of the strings, gives you a graph functionality. So really all of this is great to know, and in this particular case, our advanced static analysis concludes. And really, what I was trying to show for the sake of demonstration is that we can get to the assembly level instructions by loading this program into Cutter. And we've located that perhaps maybe these function names, these random function names, somehow have to do with the functions contained within the DLL files. All right, so that is a check mark. The next thing to do is to run through some basic dynamic analysis. All right, so it's finally time to get moving up and running with dynamic analysis, where we're going to detonate this binary and see what's going on once we run it on the file system. So I have my Flare VM where we're actually going to execute the binary, and then we have Rumnux, which is our virtual machine. It's going to impersonate our DNS service and kind of act as a C2 server for us. If you're in the AWS Cloud Lab, you should have inetsim up and running already. You won't have the ability to actually log into the inetsim instance, but you will have the impersonation of the DNS service. Make sure that you can go to google.com and you should see an inetsim webpage. Here, I'll show you that in a moment. But for the time being, let's proceed to exit out of Cutter. Can discard changes. So right now, I still have internet access after downloading Cutter onto my machine. It's time to cut this off. So going into network settings, host only adapter, and clicking proceed OK. And then in Rumnux, I should already be. All right, so in Rumnux, I'm already in Ethernet adapter 3. So before running this binary, I am going to take a quick snapshot. As mentioned in the lecture slide settings, we're going to be using several programs here in our dynamic analysis capabilities. So the first one we're going to run is on Flare VM, and that is going to be Procmon, or Process Monitor. So based off of last time's video, Procmon should be installed in our sysinternals folder within the tools section. I'm just going to run the regular version, click agree, and then yes. Alrighty, so now you should start seeing some output, and it's going to collect events, and as long as you have Process Monitor up and running, it's going to be collecting events. So what we can do is detonate this malware pretty quickly, but the last thing I'm going to do before that is going back into Rumnux and just configuring inetsim. All right, so the DNS service is running. To confirm this, we can just go to google.com. And here is where I was referring to that standard inetsim webpage. You should be seeing this if you have inetsim running in a virtual machine, or if you're in the AWS cloud instance. You should see this default. So let's exit out of here, and well, it's time for detonation. Alrighty, so a quick click here. Looks like Adobe Flash Player is going to install. Okay. Alrighty, so it appears that it tried downloading and then the binary deleted itself. And that's some interesting behavior. So something is going on where it deletes itself after probably establishing some sort of persistence mechanism. So Procmon has a lot of cool features, and one of the features that you can see is this process tree. So if we hover this over this icon, we can see the processes and the parent processes and the child processes. So for example, when we scroll down here, all right, so we're seeing all of these processes, and if we proceed to the bottom in my instance, you'll see something. Well, it appears that invoice.exe is still running somewhere, and underneath this has a child process of install Flash Player, which installs the Flash Player executable, which is quite interesting. And then you can see that we have cmd.exe followed by a console host program. So the conhost.exe binary allows us to have a console host or a terminal session. But as you can see by its fuzzed out, it looks like it's perhaps maybe in a suspended state. If you click on conhost, you can actually see the command that was run. I don't know what this exactly does, but something to take a note of. So as you can see here, it appears that it's using the temp folder to place the install flashplayer.exe. Let's proceed to actually locate this and see if it's still on our file system. So here we have the install flashplayer.exe. My gut tells me that this maybe has something more underneath it. We'll have to see later. But it does drop this, and we can collect all of this information from the process tree. So the process tree gives us some granular information into what is going on underneath. I'm going to grab this as a screenshot and collect this in our little evidence section for our malware report. All right, so let's close out of the process tree. It looks like what happens is invoice drops install flashplayer.exe, which is installed in this temp directory. It attempts to maybe download a legitimate copy of Flash Player, and once Flash Player is installed, the executable will delete itself from the desktop. And then it also spawns a console host and attempts to run this command in the background. Console host's capabilities include running a invisible terminal session, and there are legitimate use cases behind console hosts. So let's take note of this command here. In fact, I'm going to do another screenshot for this console host. I don't know what this is or if it really is going to yield any results, but something to take as a notable artifact. Another cool capability of Process Monitor is filtering tool, and it gives you some pretty granular controls into what you can filter. So you can see that we have path. Well, we can also do operation, and we're going to do a few of these here today. So let's go. So the first one I want to use is process name and proceed to do contains invoice and add that to our filtering criteria. Next, let's see what is going on within that temp path. So scrolling down to the path, we're going to say it contains, and I'm going to use that temp path that we found rather. All right, so this path here, I'm going to copy that path where the Flash Player binary was dropped. Add that in, and I'm going to click apply, okay, and see what his results are going to give us. All right, so scrolling down, we can see what's going on here. So it appears basically what is happening is, I mean, of course, we know the install flashplayer.exe is being installed. Here's another thing that was written, the MS image 32 DLL. And it was written by the process name of invoice. So that's maybe something else to take note of. Let's go back into our directory location and try to find that DLL. Here it is. So these are some interesting programs. And in fact, what I'm going to do is copy both of these, which were written by the invoice process. I'm going to copy them and paste them into our desktop. Now, it looks like they're in some sort of suspended state because they're grayed out here. But I'm going to probably upload these to VirusTotal to see if these have been flagged as malicious binaries or DLL. I don't know, but it's something to take note of. Another really cool thing about Process Monitor is we can go back into the filter criteria and we can filter by different types of operations going on. So let's go to the operation, if I can find it. And again, let's do contains. Now, I want to see if there were any sort of registry keys written by the invoice process. So there's this operation within Procmon, and it's called, I'm referencing my notes on the other screen here. Oh, what is it called? Okay, it's called reg set value. So I'm going to add this, and I'm going to take away that the path criteria. All I need to do is just uncheck the path. Again, it's apply OK. All right, so these are the different registry keys that were set by invoice. Proxy bypass, auto detect. So this is quite interesting to me here. We have these two processes, a OneDrive process and a Google Update process. Again, it appears it's trying to go into the local directory within app data. So going back into our process tree, let's see if the Google Update executable is running somewhere. And it does appear it is. It appears it's running in a suspended state, and we have, once again, all of these different executables as child processes to the Google Update. Here's another one. The parent process is WinInit, which is on Windows Startup. So what I suspect here is under the WinInit service and within Google Update, each time that Google Update is executed, perhaps invoice is also executed. And this is establishing persistence for the malware so that, if a user were to delete the invoice, it's still going to be executed underneath this different process, which in this case will be under Google Update. So once again, it's time to create a screenshot. And this is just all what I suspect at this point. All right, so what we have done here with Process Monitor is what they call host-based indicators. Basically, we're looking for any telemetry on the host that we executed the binary on. So in this case, we gathered a few screenshots worth of information, and I'm not going to proceed further, but if you're wanting to, you can continue to investigate the data within Procmon to see what other types of information that this Trojan in particular has written to disk. These are the notable artifacts that I found during my first round when I was going through Zeus banking Trojan. These were the most, I guess, highlightable things that you should use. These three here were the most interesting to me, and I think they're the most relevant because we can understand where it establishes persistence, what other files are dropped to the file system upon execution, and within this con host, you can see that there is a suspended terminal hidden session behind the screen executing some sort of command. All right, so for our next collection of information, we are going to try to see if there is any network-based indicators. What this basically means, as the name suggests, is we're looking for perhaps any network connections, hard-coded IP addresses, URLs, maybe that correct.com that we had seen within our static analysis. And we're just trying to see if this binary reaches out to any sort of C2 server. So here I have my zip opened, and I'm going to drop this back into the desktop, given that the binary deleted itself. Alrighty, password is infected, and going back down, I'm just going to ensure that inetsim is running. We have DNS server, simulating DNS service. All right, so in this case, I'm going to go down and look up Wireshark. And I want to collect network packets on the Ethernet adapter. Minimizing out of Wireshark, executing invoice, going through the Flash player again. All right, so within Wireshark, I'm looking for anything that stands out to me, anything in particular. So this sticks out to me right here. You have an HTTP request, 2 of them. One of them is a GET request to Get Flash Player. If we go down to the payload, you can see that there is this hard-coded domain, fpd-download-macromedia.com. All right, so right-clicking and following the TCP stream, this is interesting to me. So I'm going to take a screenshot of this, add this to my report as a network-based indicator. Now back on my regular machine here, I'm going to go to VirusTotal, and I'm going to look up the fp-download-macromedia.com. So it appears all of the security engines have flagged this as okay, besides this one. I'm going to go to the Wayback Machine. So it doesn't appear that this is being resolved on the Wayback Machine, at least in my case. So what I'm going to do is go back into my Flare VM machine, and this definitely is interesting to me. I definitely think this probably has some sort of second dropper. Perhaps it is downloading the Adobe Flash. I'm not really sure here. So nothing else seems really out of the ordinary in this case. There's no hard-coded DNS requests. So minimizing out of here. Okay, so at this point, what I'm going to do is turn my internet connection back on within Flare VM. Okay, I need to turn off inetsim, and then this should be able to load. Once VirusTotal is up, we can do fp download. All right, so that's good. All right, so I have internet access back on my Flare VM machine. I just looked this up again in VirusTotal. We're going to upload those 2 files, but before we do that, let's go into PowerShell and do an NS lookup on this interesting domain. So here's the name server, and here are the addresses. I'm going to copy the IPv4 address onto here, and if I can go back, I'm going to search for this IP Looks like it's clean by all security engines. I'm going to proceed to navigate to fpmicromedia.com. So here on any.run, which is a malware analysis report, I just looked up fpmicromedia.com, and actually when we input it into our URL on Flare VM, I'm getting a helpx.adobe.com. Looks like it's a legitimate web page here, not something that's trying to be impersonated. So perhaps this fpmicromedia.com is something that Adobe owns. I'm not sure. Looks like that is a legitimate website. So it perhaps is just gathering the installation of Adobe from fpmicromedia.com. So this may not be a hard-coded URL that's actually having any sort of C2 server communications. This is a quick insert clip here. I wanted to highlight a couple of tools that you can use when you have found potentially a malicious domain name. One of them being the Whois database. So Whois has a database full of information on domains. For example, remember the correct.com that we got. We can search this up and we can see the registrar, when it was registered on, and maybe the individual's information who registered this address. In this particular case, it's all not disclosed. There are services out there that basically hide or mask this information. The next is passive DNS. Think of passive DNS as a means of historical information on DNS record. So here again, I'm on correct.com. It gives you some of the similar records compared to Whois, but you can also go to the historical data tab here. And this is behind a login wall here, but you can see the history if you were to log in. Now, there are different various passive DNS tools. Some of them you have to pay for, but this gives you more historical context into who is registered the domain and perhaps when it was. So if it was something that was recently registered and it's a malware sample out in the wild, well, that would definitely be an indicator that perhaps this is the C2 server. So just something to highlight and note, something I skipped over. And yeah. The next thing I want to do is go back into VirusTotal and let's upload the files for the ones that were dropped when we executed the invoice. So going to desktop here, let's do the DLL first. Alrighty, so look at that. As we can see, this looks like some sort of malicious DLL that's going on. That's definitely something to take note of as a snapshot. So the DLL has some sort of malicious capabilities. Let's upload that install Flash Player binary as well. So it does appear that the installation of Flash Player is legitimate, and my hypothesis is that it's going out and downloading that, perhaps through fpmicromedia.com. But it does drop this malicious DLL file, which contains some interesting functionality. I don't know what it is, but it looks like it's some sort of Trojan. I'm guessing that this has to do with Zeus bot in particular, but perhaps this could be used from other different virus variants. All right, so in this case, I understand that, well, we haven't done a ton of dynamic analysis, but we can get at least an overall picture of what is happening. The invoice is downloading some different programs, specifically install Flash Player, which seems to be legitimate binary, but it also downloads a malicious DLL file. In order to establish persistence, it looks like it has a Google update, and it infiltrates the Google update binary. So every single time Google Chrome is updated, the binary or the invoice file will be executed. And then finally, the fpmicromedia.com. This is the only domain that I could extract during my analysis. I didn't see the correct.com, which is interesting. but it appears that that is a legitimate domain. All right, so for our last step, we're going to be creating a YARA rule, which allows us to fingerprint this particular variant. Back on my Flare VM machine here, I'm going to open up Notepad++. So I'm going to write my YARA rule here in Notepad. You can do it whatever you want to. Now, YARA rules are broken up into blocks, starting out with the keyword of rule. You can give it whatever type of name you want to. So in this case, we're just going to give it the Zeus name, and within the brackets, there's mainly three different blocks. There is the meta block here. There is the strings block, and then the condition block. So for our meta block, what we're going to do is write who authored this, and in our particular case, it's me. Now, you don't have to provide the meta block, but if you are going out and analyzing some malicious sample in the wild and you want to have credit for what you've done, this is a great way to provide credit. I can also provide a description. In this case, I have written it as a detection rule against the Zeus banking Trojan version. All right, so inside the strings block, this is where we can provide any sort of static information about the binary or malicious executable. In our case, there is a few things that we could perhaps note. First is the file name. So variables are assigned the $sign followed by the name of the variable. In this case, I'm going to call it file name. And here I'm going to supply within our report the specific file name. Now, after this, I'm going to supply ASCII. This denotes the type of encoding used. All right, so next, let's proceed to write out a variable for those suspected function names that we exported from our static analysis. I'm just going to be using one of the function names. So first, let's add in a comment. Let's do it suspected name of functions. So a // will denote a comment. And here I can actually provide the function name. We're going to call it all right, so going into our report, remember that we got this interesting string cell to roto king high, whatever this is. So I'm going to add this as a unique string within our YARA rule. Now, you're more than welcome to continue to add whichever function names from the report that you want to within this YARA rule. For now, I'm just going to add this particular string. Next is the PE magic byte. You don't have to do this, and there are libraries within YARA which can see if it's a portable executable or PE. So as I said, the MZ initials denote a PE or portable executable, and I'm just going to add that in as a rule. Finally, we can add in different types of hex string sequences if we want to. In this case, I'm just going to write hex string function name. And going back into Flare VM, which we are already in, Let's open up HXD. So this will give you a hex output of file contents. I'm going to proceed to extract the invoice again and upload this into HXD. All right, so here you can see all of the hex output. Now you're more than welcome to add whichever type of hex sequence you want to. You can see the decoded text here. If we do a Control F, go into our report, let's see here. So here is those interesting function names. I'm going to add in this hex sequence right here. All right, and I copy this and paste this. So there is all kinds of different ways that you can show and denote different types of information within YARA. Here are just a few different ways. Now the condition block actually evaluates upon this logic within the strings. So you can write some pretty complex conditions if you want to. For this case, we can just go ahead and say, okay, this is what this must contain in order to meet the Zeus rule. All right, I'm going to write PE magic byte at position 0 and file underscore name. Next, I'm going to have an AND condition and say it also must contain the function name kernel32 string or the hex string So what I'm doing here is the following conditions must be met in order to meet the Zeus rule. The PE magic byte, which of MZ, must be at position 0 within the file. The file also must be renamed this particular file name. Next, the following strings must be in the binary. One, it could be this string here, or two, it could be this string. So what this means, it could be either this one or this one. And these are just unique strings within the binary, which denote perhaps that this is meeting the Zeus rule. So this is a really basic YARA rule, but it kind of shows the basics of what a YARA rule does. It's for detection. So we're going to go up to File and Save As, and save this onto our desktop and call it Zeus.yara. Okay, so here we have our Zeus YARA rule. I'm going to go into Commander. Skip the download. Go into the desktop. So embedded within Commander is this program called YARA64, which allows us to supply a YARA rule followed by the malicious binary. So here I have the Zeus.yara rule, and we're going to follow that by our invoice, the name of the binary, and then provide some different options here. So the S will print match strings out, the W will ignore warnings, and then the P will allocate 32 threads to this rule. So what this means here, based off of this output, is that these are the rules that were matched. So at location 0x3176C, cell roto crud, whatever this byte here, And the same for all of these. So let's just confirm. For example, let's go to the 0x3176C address. As you can see here, based off of this memory address, which is 3176C, based off of this column, so starting at byte 43 all the way to 73, it's matched. So this is what the YARA 64 executable does. Basically just evaluates our YARA rules and it lets us check if we've got it correct. So at this point, we have conducted and concluded our analysis. Finally, we can go through our report, polish it up, and provide little descriptions for each of our screenshots if we wanted to. For the sake of this video, I'm not going to do this, but when you are in a real-world situation, you are going to go out and explain what is happening in each of these screenshots. So within the basic dynamic analysis, we could talk about how we see these malicious DLL files, the URL, and anything else really. Okay, so this concludes our basic analysis of the prolific Zeus banking Trojan report. Hopefully you've learned something new. Hopefully it's been, some sort of educational. I know this is kind of a basic analysis. We haven't actually gone in and done any sort of reverse engineering. This will definitely equip you to go out and dissect your own malware variants, whether that's on the zoo or anywhere else that you find. Just always make sure to be practicing safety. So this concludes Part 3 in the Complete Malware Analysis Project 101. Hopefully you have enjoyed this series. We've learned something new, and I certainly have. And well, yeah, I guess until the next series of projects, have a good day. And don't infect yourself with malware.